Now let's think about the acidity, and then we'll go to basicity of carboxylic acids. Now, if you look at a carboxylic acid molecule, there is an acidic proton bonded to the oxygen in the OH group. And so here's an example. We'll go back to acetic acid. So vinegar is an acidic solution, and acetic acid is the main ingredient in vinegar, the main acid in vinegar. So this is acetic acid. If you look at the pKa table, the acetic acid pKa is about 4.8. So not a super low pKa, but definitely an acid, definitely acidic pKa. So if we had a base present, like hydroxide, and it removes the acidic proton from a carboxylic acid molecule, in this case acetic acid, we can show what this conjugate base looks like. This helps us understand why the pKa is relatively low. So oxygen gained a pair of electrons from its bond to hydrogen, and we have H2O as a byproduct, or as a conjugate acid. So in the conjugate base of acetic acid, and really any carboxylic acid, that negative charge on the oxygen atom is a delocalized charge. So a pair of electrons can create a double bond between carbon and itself, and then between the oxygen, and then we can break that pi bond. And so we have resonance structures here. We may have even used this molecule as an example in the past to discuss why this acid is a relatively strong acid, and that's because the conjugate base is resonance stabilized. And you might remember a more stable conjugate base means we have a stronger acid. So the acidity of a carboxylic acid is more acidic, or in other words, carboxylic acids have a lower pKa than molecules that have an OH group without any possibility of resonance stabilization in the conjugate base. So something like ethanol, I don't have the pKa of ethanol memorized, or propanol here, but it's certainly higher than acetic acid because its conjugate base is not resonance stabilized. And now the groups that are bonded to the carbonyl carbon can impact acidity. So here are two examples. We'll compare to acetic acid. So acetic acid has a pKa of 4.8, and then we'll look at these two examples. So trifluoroacetic acid, you might predict if its pKa is higher or lower than acetic acid. And then formic acid, this molecule here. Trifluoroacetic acid, we have a fluorine, which is an electronegative atom, pulls electron density towards itself through the inductive effect, and that increases the partial positive charge on hydrogen. It also contributes to stabilization of the conjugate base. So trifluoroacetic acid is a stronger acid than acetic acid. Its pKa is about 0.23. And then formic acid with a hydrogen bonded to the carbonyl carbon. We're comparing to acetic acid. We have a methyl group versus a hydrogen. A methyl group is more electron donating. So having a hydrogen instead of a methyl group means that there's lower electron density throughout the molecule, and that increases the acidity of that molecule, which means that we're decreasing the pKa. So the pKa is slightly lower, about 1 pKa unit lower, 3.75 for formic acid. Now, if we had an even stronger electron donating group bonded to the carbonyl carbon, its pKa would be a little bit higher than acetic acid pKa. Okay, lastly, we'll talk about basicity. So we'll redraw carboxylic acid functional group. Now in this molecule, we have 2 locations where there are atoms with non-bonding electrons. So potentially 2 locations that are basic. But one oxygen is more basic than the other, and to determine which oxygen is more basic or where the more basic site is on the molecule, we need to draw conjugate acids. So we'll draw one conjugate acid where we protonate the carbonyl oxygen and another conjugate acid where we protonate the OH oxygen. So first, if we protonate the carbonyl, we have a new hydrogen bonded to the carbonyl oxygen. That oxygen is positively charged. If we protonate the OH group oxygen, we have a positive charge on that oxygen and an additional hydrogen there as well. Now, both of these molecules have a positive charge, but in only one of them, the positive charge is delocalized. If we look at the molecule up here that I just drew that arrow to, that positive charge is localized to the oxygen, and there isn't any resonance structures that we could do, that we could show that would transfer the ownership of that positive charge to a different atom. The positive charge here is localized. Now, if we look to the molecule drawn towards the bottom of the page here, this positive charge is delocalized. The oxygen from the OH group can share electrons to create a double bond there, and the electrons in the pi bond can resonate to be owned by the carbonyl oxygen. And so the resonance structure our carbonyl oxygen is now neutral, and the OH group oxygen, the oxygen that was originally the OH group, now has that positive charge. So this positive charge is delocalized. when carbonyl oxygen is protonated. So that means the carbonyl oxygen is the stronger base. It's a stronger basic site. It is not impossible to protonate the OH group oxygen as we drew here. But if we have one equivalent of a base or a weak base present, then it's going to protonate the carbonyl oxygen before it would protonate the OH group oxygen.